it, okay?
Yeah.
Oh, sorry?
Yep.
Okay.
This is Dr. Ank, who's going to show us the Ventrain. Go ahead. Yeah.
Okay. So, this is a baby lung. Of course, we know this is a pretty bad model of a baby lung because this glove has a very good compliance, whereas a baby lung has a pretty bad compliance. But anyway, we want to demonstrate a compliance-independent ventilation effect through this straw, which is, I think, 45 centimeters long, outer diameter 2.66 millimeters, inner diameter 1.66 millimeters. So get your glasses if you want to see the lumen, okay? So first of all, just to demonstrate what flow resistance means, I'm blowing up this glove, okay? To the extreme, look at this, okay? I'm disconnecting it, and you see it's not that much deflating. To get the air out, you have to do this. Okay? Now you can do it differently. Now first, the flow is here set to 6 liters. And what's this? Most likely this is all you need to do if you have a baby case. And if you overinflate slightly like this, you can easily bring back the volume to a reasonable amount by a little bit more aspirating. Again, overinflating like this, oops, and now actively desufflating. And then starting again.
So I guess the key word is the concept of active deflation here,
yeah.
Right?
And you see, the device is activated by occluding this. If this opening, the so-called on-off switch, sort of a bypass where air is expirated from the outside, is open, the device is functionally switched off. When I occlude this opening, it will start to suck, as you see here. And if I simultaneously occlude the on-off switch and the outlet, I'm redirecting the flow set at the flow meter to the patient.
And there's a simple sort of, I shouldn't say simple because it's physics that I don't understand. So what's the effect that gives you that sort of expiratory phase here?
Now, actually, Ventrain is also a high-pressure device. It is important to know it is flow controlled, so you can easily estimate how much volume you are administering over time. For example, I've now set the flow to 6 liters. That means if I redirect the flow for 1 second to the patient, it means insufflation of 100 cc, okay? But anyway, the gas is pressurized in front of the jet nozzle, which is here inside the Ventrain device. And at the jet nozzle, high pressure is turned into flow velocity. And this is actually Bernoulli's principle. You know, by increasing the dynamic pressure of a gas flowing, you are decreasing the static pressure. And this is Bernoulli's principle. That actually is the principle why planes are flying, which are actually sucked into the air. Yeah? Okay.
That's great. And can you just show me the catheter that you've used with this? It's sort of a kink-resistant catheter here.
I stopped this for a while.
Yeah.
Now, this, what I've demonstrated yet is applicable in children, small children. This cannula is intended to be used in adults. It is a specially designed, a dedicated needle cricothyrotomy catheter. It has a sharp stylet. And the neat thing is it has sort of a movable flange. And look at this, I can bend this catheter pretty extreme without kinking. That's the back. So this catheter, which has a pretty thick wall, a lumen of 2 millimeters, length of 75 millimeters, is most likely not to kink during insertion or while being inserted.
So I guess this in part is dispelling the myth that you can't ventilate through a small bore catheter
right
here.
Yeah. Okay. Yeah. If we are the mythbusters right here, that's a nice idea. Yeah. Indeed, the myth is you can't ventilate through a straw, and you've seen actually you can.
Right. Well, that's great. Thank you very much for your time.
Okay, thank you.